Momentum 3. Conservation of linear momentum with particular reference to explosions. And we're going to not only cover explosions but collisions, but that will be in the next video. Now, what do we mean by the conservation of linear momentum? Well, by conservation we mean that nothing is lost, and so we use the term a closed system. We're going to look at very simple explosions and collisions where you might take one thing and it blows apart into two things, or you take two things and they collide and stick together to become one thing. That's a collision. Now, in the real world, explosions and collisions are never that simple, and therefore we mostly could not model them as closed systems because things are lost. We can't keep track of all the mass, and we can't measure the velocity accurately. But because we're using a simple closed system, the change in momentum is zero. Now, there are some situations, complex situations, where they are closed systems. For example, at CERN in Europe, where they have the Large Hadron Collider and they collide particles together, such as protons and neutrons and antineutrons and all sorts of things, they happen within great big sensor arrays, and every particle, every ounce of energy has to be accounted for. Otherwise they can't track new particles, like they recently announced they had found the Higgs boson. They couldn't do that if bits were missing, because it wouldn't stand up to any examination. Therefore it's a closed system. But for us, we keep it simple. Now, the law of conservation of momentum, however, applies to every collision and explosion. It's just that we can't model it all the time. But we're going to apply the law to very simple situations that we would consider a closed system. And we're calling them linear momentum in that it's all happening on a line. Okay? We just keep it simple, happen on a line. Collisions are actually three-dimensional, of course, but we simplify it down. So, what are we talking about? Explosions. So this is when a single object separates into two or more fragments. And so there's a bomb at rest, represented by a sphere. That's our initial momentum, and we should see that because it's at rest, has no momentum. And then we blow it apart. That's the center of mass. There's the mass 1, there's mass 2. Those two masses add up to our initial mass, and they've got opposite velocities. And so we would have to say that the initial momentum equals the final momentum. And that's the law of conservation of momentum. So let's consider a 10 kilogram bomb. Initially it's stationary, so the initial momentum is zero. It explodes into two fragments. We have a 4 kilogram piece travelling west at 15 meters per second. We must therefore have a 6 kilogram piece travelling somewhere. We don't know. We're going to work that out. As it is a closed system, the momentum before the explosion must equal the momentum after the explosion. So our question is, what is the velocity of the 6 kilogram piece? Now, if we were to draw this is our before. Alright, so we have our bomb and it's 10 kilograms, it's 0 meters per second. And then our after, we have a fragment and it's weighing 4 kilograms and it's traveling west at 15 meters per second to the minus 1, and therefore we must have another fragment which is 6 kilograms, but we want to know what velocity it's going at. Now, we could probably guess it's going to be moving to the east, but we need to quantify that, so we need to calculate it. Now, here the momentum is 0. P equals 0, and that's the initial momentum, that's a 0. Therefore, this momentum here must also be 0. That means that the individual momentums of these two fragments must cancel each other out to give us 0. And so this is why we did vectors, and this is why we have a direction as well. Okay, so these sorts of diagrams help you understand So it's a good idea sometimes with questions to draw a diagram like this, a before and after picture, and it helps you work out where to put everything. So, whoops, let's get rid of that, and let's go to the solution, and this is the math solution. So the change in momentum is 0, so the initial momentum equals the final momentum. They've done a little bit of maths here. They've got mass 1 and mass 2, because that's the total mass, 10 kilograms. Initial velocity 0. There's our 10 kilogram. There's our 4 kilogram mass travelling at 15 meters per second. There's our 6 kilogram one, and there's V2, our unknown. Now we have to be careful with our signs. So we're saying that to the west is positive, because we've got a positive sign there. And so when we solve all this, we get a negative answer. And so that's in the opposite direction to west. Therefore it must be to the east. Okay? Not too hard, just have to be careful with our signs. Let's do another example. And here we have a boy on roller skates. Let's draw him. A boy on roller skates. There we are. He's a boy. He weighs 60 kilograms. He's carrying a school bag. So he's got a school bag there. Looks like a shield, but it's actually a school bag. And that's our before. Now he's moving. So he's moving. Which way is he moving? Doesn't say. He's going at 8 meters per second to the -1. He weighs 60 kilograms. And his bag weighs 10 kilograms. Okay, so that's what we've got. And afterwards, he throws his bag directly forward. So he's still on the roller skates. Whoop, whoop. Should have made a simpler diagram. He throws his bag forward. Okay, so there's our 10 kilograms. It's travelling at 20 meters per second to the -1. He still weighs 60 kilograms, but we don't know his velocity. Okay, now here, instead of like in the previous question, we said our initial momentum is equal to 0. Well, that's not the case here. We do have an initial momentum, and we can work that out fairly easily, because P initial equals mass 1 plus mass 2, because we've got two masses, we're going to add them together, times by V, and in this case it's going to be 60 plus 10 times by 8, and I'm going to cheat, look over here, that's going to give us 560 kilograms meters per second to the -1, and that's going to be in which direction? Let's call it to the right. Yeah. Well, we're saying to the right, could be to the left. You could have drawn your diagram to the left. There's no frame of reference, so you can create your own frame of reference. Now that's going to be the initial momentum. So that's got to equal the final momentum. And the final momentum is made up of two momentums. It's going to be the momentum of the boy plus the momentum of the bag, and the momentum of the boy is going to be 60 times by V, let's put that in brackets, plus, and we know the momentum of the bag, it's going to be 10 kilograms times by 20, and so if we move all that around, remembering that this equals 560, so we can solve that, and we would get a V of 6 meters per second to the -1. Now this is positive, just as this was positive over here, and therefore the boy is still moving in this direction, because we've determined that that's his original direction. So he slows down. So imagine you're skating along, you have your heavy bag, you throw your bag forward, it slows you down a little bit. It's the law of conservation of momentum. Okay, let's have a look at what that would have looked like maths wise. Here they go, you can pause this and read exactly what I did, but I drew a diagram. Okay, so that tells us positive direction means that the boy would continue enough to move forward, whichever direction is forward. So now you should be able to do questions 7 and 8. Now, some examples. Some examples of collisions and explosions, to put it into context before we move on to collisions, is cars. Cars can explode and collide. Billiard balls. If you've ever played pool or billiards or snooker, it's all about collisions and explosions. What do you mean by explosions? Well, when you fire into the rack of pool balls, that's like an explosion. Hammering in a nail is momentum, is a collision. Cannon firing is an explosion. Then on the OneNote you'll find a whole lot of videos that give you real life situations, and I want you to watch those, but when you watch them, don't just go, oh, that's interesting, or, wow, big explosion. I want you to think, where's the momentum, where's the forces, what's happening, is this an explosion or is this a collision, is momentum conserved, how would you work it out? Alright? So in the next video we're actually going to look at collisions. See ya!